All right, welcome back from the break. This is CS3510, L05B, right? And this is a quick thing on Heaps. It's just about sort of the runtime. Recall what we did. We just finished Dijkstra's algorithm, but we didn't analyze its runtime. So it turns out that the runtime of Dijkstra's is data structure dependent. So we're just going to kind of give a brief review of things you probably have seen before about how binary heaps and stuff work. But before that, let's analyze the runtime of Dijkstra's algorithm. I didn't erase it. I still have it here. Certain operations take different time depending upon how long each of those operations take. So before we get to there, let's just count the number of operations, right? Most of the time complexity here involves interaction with the queue. Now the queue will take its own time depending upon the implementation, which we'll talk about today. But before that, let's just talk how many times the queue is accessed, right? So the operations that are hit with the queue are going to be delete mins, they're going to be decrease keys, and there's going to be a make queue operation, right? So we're concerning ourselves with how many of these operations there. There's no insertion or anything like this. Each one takes a different time, right? Just a quick review, delete min is in a priority queue, elements are given different priority, of course, and let's say they're positive integer values based upon the shortest distance at that point, and so we take the minimum each time, right? That's the delete min operation, and then it's removed from the array. Decrease key is going to be, we can update the priority of an element by updating its distance, basically, right? So we say, oh, this one we found a shorter path from length 7, now it's length 2. So its priority should be, it should be able to cut the line, go ahead of everyone, and when we want to call the minimum element, because we've decreased its key, maybe we'll call it sooner than we used to, something like this, right? And then make queue is just makes the queue. I mean, it's just like you have these unstructured objects, you just structure them, that's all it is, right? So how many times is delete min called? Yeah. So we have v delete mins. Okay? And let this be the number of vertices, capital V. It's also the set of vertices, but whatever. How many times is decrease key called? Up to E times. In some worst case analysis, each edge updates an element of, each edge is a newly found shortest path on the newest thing, which was kind of the example that we had, except for the last 2 rounds, right? And then how many make queues are there? Yeah, we're just going to make the queue once. So that's basically the runtime of Dijkstra's algorithm. Now, that's actually a more generic runtime and maybe a better runtime than giving us explicit big O. Because then you can say, well, each of these has their fixed in different implementations of our architecture or whatever. This is how the runtime would update. And that's basically what we're going to do today. So let's talk about the how would we implement a priority queue onto an array, let's say. So let's just do the array operations first. So if we have an array, let's say we have vertices, let's say v1 to vk, what we would do is store the priorities in an unsorted array. 3, 8, infinity, 0 to infinity, something like this, right? And then as we compute over the array, we cross things out, we update things. So the operations, again, are delete min. If we have an unsorted array, what is the time it takes to delete the min? Sorry? Someone said it? Yeah, it takes O of V to delete the min. Why? Sorry, what? Yeah, how do you find the min? It's unsorted. So you just got to loop over it. Oh, there's the min. Now let's say we put some kind of tick marker or whatever, some data structure dependent thing. Maybe there's a second array of booleans if you wanted to be annoying about it. You're like, okay, that one's deleted. Don't look at it anymore, right? So we would find the min, and we would quote unquote delete it or mark it in linear, basically v time, right? What about decrease key? Not quite. Decrease key takes on the heap itself, or the queue, the priority queue, the vertice, and it gives an integer value that you want to update it to. Right? So for example, if you have vertices v1 through vk, the indices correspond to, without something exotic like tuples or something, the indices correspond to the priority of that specific element. So this is the current shortest distance to v1, to v2, to v3, to v4, to v5, and v6, let's say, right? So let's say we wanted to update v2 from distance 8 to, let's say, distance 5. Yeah, what would we do though? Just to, yeah, we would say like v2 takes on this v, right? Constant time. Okay. Just go update the element in the array. Not too hard. What about the make q operation?
Isn't that sorting?
No, let's say it's not sorted. So at the beginning, during a birth, what does this look like? We have a 0 and then infinity and then an infinity and then an infinity, something like that, right? That's what the quote unquote unsorted array looks like at the beginning. How long does it take to make that? Yeah, well, yeah, it's because, yeah, I mean, it's complicated, and sometimes, like, what is the time of memory allocation? Do you have to zero it out before you do it, or do you just say, oh, here's my bounds? It's complicated. It's a good assumption to say, yeah, if you are allocating something, it takes approximately the size of the thing you're allocating, just to be safe. Now, of course, this is also something even hardware specific, but whatever. This is O of V, let's just say. So our runtime for the array is going to be O of, we have V delete mins, and each delete min takes V time. So we have V squared here. We have E decreased keys. Each decreased key takes constant time. So we have plus E plus a single make Q operation, and that takes at most V time. So here we see that the runtime of, if you use an array, the runtime of Dijkstra's algorithm is what? Yeah. Why? E is at most V squared, and in the dense sense, this is just V squared plus V squared plus V, which is O of V squared, right? So this is V squared. Now, can you do better than this? And that's basically the point of today's lecture is actually, yeah, you can. It's instead of using your priority queue implementation as a unsorted array, which actually, honestly, V squared not that bad, but you can beat it in, especially, which is especially necessary for very large graphs, right? So recall how we're going to support the operations of a binary heap. A binary heap, instead of considering the elements in some unsorted way, a binary heap has things like this. It keeps the elements in specifically a nice, as full as possible binary tree. Now, if your thing is not a power of 2, that's okay. The way the heap will work is that the last row will have as many things as it can shifted to the left, right? So the last row's rightmost element will be the last element in the quote-unquote heap. Now, the binary heap has a special property. For each element, it is less than or equal to its children. Now you could of course do like max heap and then say greater than or equal, but the heap property is preserved during the computation on the heap, in that every node is greater than its children, right? By the way, by transitivity, that tells you that if the children are greater than the grandchildren, the children are less than the grandchildren, and the parent is less than the child, then by transitivity, the parent is less than the children, and so on, right? It goes all the way down, basically for free. So, if, for example, we could have something that looks like this. I don't know, 3, 2, I don't know, 5, 7, let's say, right? So that's perhaps not an ideal looking heap, but let's say we have those few elements. That's kind of what they would look like. Now, if it was more full, if there was more nodes in there, it would look more like a little bit cut off of a more binary tree thing than something so biased on one side. But notice that 0 is less than 2 or 3, and then 3 is less than 5 and 7, and so on, right? So this is the, it's got the property, it's good, so to speak, right? Now the cool things about the heaps is that, specifically in this case, that we can implement a priority queue on top of a heap pretty efficiently, right? So we have 3 operations. The first one is going to be delete min. Cool thing about the priority queue, the heap basically is the priority queue. How do we find the minimum? If we arrange our elements instead of an unsorted array, if we arrange them into a binary heap like this, how do we find the minimum of the binary heap? Yeah, there it is. So that's the minimum. Why? It's going to be less than its children, and its children are going to be less than it, and those are going to be less than it, and so on. So by transitivity, in fact, there's a total ordering on the elements. This is less than the rest of the tree. So there's the minimum. Great. So delete min will take the minimum from the root. But the problem is you can't do that twice. Let's say you want to delete min twice. You delete that. Now you don't have a binary tree anymore. You have like some broken thing. That's not two binary trees. I don't know. How do you fix that? Does anyone remember? Yeah, so in fact, it doesn't take constant time to delete the min because you got to do a little bit of organization, put your cards in order to make sure that the next time you call delete min, things work out nicely. And the way that's going to look is, first you delete the minimum, and then you swap the last level's rightmost element with that element, right? So what's going to happen here in this specific one, it's going to go to something that looks like this. Okay. That doesn't have the heap property though. Yeah, you swap. What you do is you repeatedly swap with, now by definition, you swap parents and children from the root until you have satisfied the heap property. Now a better heuristic, and then just you have to swap 7 here with either this 3 or this 2. And then recursively do that all the way down to the depth of the tree. But the better heuristic is actually not just to swap with one or the other, or not have a decision on which one to swap with, but just swap with a minimum of these two, right? So we're going to swap with a minimum of 3 and 2, which is going to give us 2. So when we swap from that, it's going to give us 2 is going to be up here, and then we're going to have 3 over here. 5 is still going to be here, and then we're going to have 7 here. Now, does that have the heap property? Yeah. Excellent. How long does delete min take? Not quite. And I made a mistake here by not drawing a bigger binary tree. It looks like L05B because I touched like V things, but that's just because V is small. Yes. Yeah, why?
Because like you only go down one branch of the tree.
Exactly. Let's say you didn't swap. Let's say we swapped over here and not over here. This whole part still has the heap property. We haven't touched anything there, right? So if we choose to swap here, then we got to chain ourselves down. So like recursively, we're just going to have a small thing that goes all the way to the bottom. It's not going to be like everything in the heap is going to have to be touched. It's just going to be up to the depth of the binary tree, which if we have V elements is going to be delete min is going to take log V. For deleting a min. Okay. What about decrease key? Again, let's start with the same binary heap. Okay. And let's say we update a vertex. Let's say we update this one to be 1, right? By the way, we don't really need insertion as something in our binary tree, but we could use it here. We would perhaps delete the node and then reinsert it with an updated value and then do the same thing. But let's talk about how you can just simply update the key in place here, right? What needs to be done here if we just take the vertice where it's at and then change the key of it? All we have to do now is update the heap property up through the tree again, right? So we would take this one, if it doesn't satisfy the heap property, we would swap it with its children, right? This is the one that doesn't satisfy it, so we would swap that. So that is how you can decrease the key, and notice that it's higher up in the tree. So its priority has increased, so it will be picked sooner than it was before, probably, right? It's closer to the top, it's going to be picked over other things, right? How long does this take? Yeah, it's still the same swapping around, right? You just chain swaps all the way up recursively until you get to the top, right? Takes log v time. Finally, make q. There's two ways. Making a queue, I mean, like, it's kind of a pedantic discussion. You may have seen Dijkstra's and been like, why did we even talk about this? Obviously, this is not worth mentioning. But in the binary heap implementation of a priority queue, it actually does take some mentioning. There's a bad way to make a queue in a binary heap to start with, a priority queue. What's the bad way first? Yeah.
Repeatedly insert elements one by one.
Yeah, start with an empty heap and then perform an insert operation, which will proceed by a similar swapping chain. You just find its place in the tree, right? How long will that take?
N log n.
Yeah, let's say v log v, because you do v elements and each one takes at most log v to insert. So it takes v log v. That's not good. Can you do it better? Actually, it doesn't. That's not that bad either. But can you do it better? O of v how?
Build heap. I don't remember exactly. I know like you kind of do the same operations where like you're gonna have like the array of elements and then you're just gonna look at the parent and compare it to the children and then keep going down.
I'll tell you, it's simpler than that. And this is not in general. This is specifically for, oh, I see. So there's, in a general priority queue implementation, I think something like that would work. But actually, we can get around explaining anything about a priority queue and being specific to the case that we're in Dijkstra's. Specifically in Dijkstra's, why does make queue take linear time here? Yeah. There is no priorities. They're all, I mean, here's what the priority queue is going to look like. Right? You're not actually like, it doesn't matter. I mean, you know the root already because that's the start. It's single source, so it's this 0. Everything else, don't matter yet. I mean, just they're all infinity. Now, as you, of course, perform decrease keys and delete mins, of course this is going to update. But at the beginning, doesn't matter. You believe you could construct a binary tree of v elements in v time, right? So that can be done faster than insertion, simply because you know that it starts this way. It starts in a very simple way. Now, you can actually do it in the general case, you can also beat v log v. But, I mean, that's clear. I mean, obviously, this is basically unsorted stuff. It's just like it all works out nicely, right? So how long does make queue take then? O of v, right? Okay. Let's contrast that runtime with our array. So we mentioned that, and this is for the array, and this is for the binary heap. Delete min in a array takes v, but in a binary heap takes O of log v. Decrease key in a array, an unsorted array, takes constant time, but here it takes more. It takes log v time. And how long does it take to make the queue? Probably the same. Right? So what's our runtime for the binary heap? We have v delete mins, and each one takes log v time. So that's going to be, it's going to be v log v, plus we have e decrease keys, but each decrease key takes log v time. Plus one make queue, which is v. Now what is that? It's going to be O of v plus e log v. Something like that, right? Is that better or worse? It kind of depends. When is it worse than the array? Suppose the graph is dense, right? Let's say v is approximately e squared. Sorry, e is approximately v squared. Which one of these is better? Yeah, if v is approximately, if e is approximately v squared, if the graph is dense, then the array takes O of v squared time, but then the binary heap implementation of the priority queue will take O of v squared log v, right? That's worse. So the binary heap actually doesn't work on the dense graph as fast as the array does. When but what if E is approximately V, right? Then this one, then the array is still going to take O of V squared, but the priority queue is going to take approximately, the binary heap is going to take approximately, what, V log V, right? So if E is smaller, if the graph is pretty sparse, then the binary heap wins, and if the graph is pretty dense, then the array wins. When does the trade-off happen? When is the exact moment you would choose a binary heap priority queue over a array priority queue, an unsorted array? Yes? Yeah, E is approximately V squared over log V, right? Like if it's any less than that, then you'll choose the binary heap, and if it's any more than that, you'll choose the array. Now here's the thing. Most graphs, and we mentioned this already, but most graphs in practice, overwhelmingly, like in every use case you'll ever find them, it's going to be sparse. They're going to be closer to here than they are to here. Question?
If it's more, choose array.
So like, it takes time for you to even discover if the graph is dense. So let's say you had you're writing a high performance library. If the graph is dense, do this version. If the graph is sparse, do this version. Or just be lazy and just do the binary heap every single time and hope no one will ever run it on a dense graph, which happens, I mean, like in practice, most graphs are sparse. So it's like heuristically, just like it's okay, you know. Now, do know that there is a trade-off. The moral of the story here is that although algorithms, we pretend it's like independent of data structure specific things, and we're like, oh, look, so that's like, we can just say it's O of n, or like wave our hands around and stuff. It's never really true, and these kinds of data structures don't simply change things that are hidden away by the big O, like constant factors and so on, right? They actually can make a huge difference in the actual runtime. And in fact, these are not even the best. This is not even the best priority queue implementation for Dijkstra's. There's another more complicated one that we haven't talked about called Fibonacci heap, which is like O of V log V plus E, something like this. I don't remember exactly. But complicated heap implementation, complicated priority queue implementation on a Fibonacci heap runs even more efficiently. So you can't just say for certain, like the way you could for merge sort or something like, oh yeah, n log n. It's very dependent on how it's implemented. That doesn't detract from, I think, the elegance that is Dijkstra's. It's such a simple algorithm, but the fact that it through very simple properties, it gets you the shortest path in such a way, I think it's something that's pretty beautiful. So, questions? All right.